Okay, now we're really recording. Okay, so this is like where we left off, right? Couple of things here to note. Like, yes, I know in the lab we did something where we connected an input toggle switch directly to an output, which when you turn it on, it turned on. When you turn it off, it turned off. And that's effectively what this configuration is doing as well. But it feels like, well, there's a lot of extra steps. Why? Well, you'll see, it'll hopefully become very clear shortly why we're thinking about it like this. But the key thing here is this part of the circuit and this part of the circuit are entirely separate. I know that this part has an impact on this part. Whether or not this is on or off changes the state of this thing. But like if there's a charge here, the charge on this line never goes anywhere down here. It would be whatever is up here. This part and this part separate. Also, with this particular configuration, the value up here is always on. It's always 1, and down here it's always 0. Well, really down here it's always 0. And then when I turn this on, then the charge can go down, right? And we talked a little bit about like the necessity of that pull down resistor, how it's kind of like if we put some like wadding in the drain of a sink. You turn on the tap, the water still wants to flow down the drain, but it can overflow. The overflowing outside of the basin would be like the charge going down here and backing up and then flowing out to here. But as soon as we turn off the faucet, the water will eventually just drain out back down to 0. It happens really fast with like electricity, but that's like the idea there. Any questions about this? I know it feels like we're just like, okay, you want to turn it on and off and you're using all of this stuff to do that. Yeah, we'll see. Really, it's to keep the inputs and the outputs separated. Okay, all right. When it's not on, we could see in digital, like it visualizes this as like a bright green. When we turn it on though, and it even shows like, kind of like the state of this transistor, how it's like an open switch. And then when we turn it on and there is a charge, the state of the transistor changes such that it's a closed switch. Pretty neat, right? And then we get the current out there. Questions, thoughts, concerns? Or does this make perfect sense? This is, yeah, obviously I get it. All right. All right. Now on to logic gates. With clever configurations of that basic idea of switches, by configuring, like adding a few more and configuring them, we can start to perform the logical operations that we care about. Specifically, I mean, we can do all of the ones we've defined so far, but we're going to start with our AND, our OR, and our NOT. And we're going to build these with these transistors, just in clever configurations. Now, warning. There are more complex configurations that we could use to generate the gates we're about to talk about. And if you use the textbook for the class, you will see these more complex configurations. When I say more complex, I don't mean like they're overwhelmingly bad. No, it's just there's more to them. And you definitely are capable of understanding what they're doing just by looking at them and taking a moment to think. You'll figure it out. But we're not going to use these more complex configurations. The reason that the textbook uses them is because in practice, due to the physical limitations of how all of this stuff works, they kind of have to like engineer these designs in such a way to make sure it works in reality. But digital is working in an idealized world where some of these limitations don't exist. So we don't need to over-engineer it. We could, but we don't need to. And so I'm not going to because it's just, it doesn't, I don't feel it adds anything to the underlying idea of what we're doing because like by using these simpler configurations, what do I say here? By using the simpler configurations, we're not losing anything because one, the abstract ideas are the same. Okay? The more complex configurations are only necessary because of the physical properties of semiconductors. And for the most part, we're also not really going to be directly interacting with transistors in this course. Only for this early part of the semester are we going to be doing that. So we really don't need them. And if you're thinking like, oh, okay, the point of the course is how we can build computers with these basic Boolean operators, not how we build them with our physical things that are constrained by our physical reality. That makes sense. So we're not worried too much about that. So we get to deal with like the simpler configurations. And when I say simpler, I mean like these are the idealized ones. Like this is what you would want to build, but we can't do it just this way because of reasons. So we add this other stuff to it. We're going to be focusing on the ones that are like really the spirit of what we would want. Okay? Okay. All right. Okay. Just as a convention, I'm going to try to follow this. I might break it. Going forward, words for Boolean operators and logic gates will be stylized to help designate what I'm like referring to, because sometimes it can be confusing if I'm saying like and or, you know, like it can be weird. So I'm going to change like typesetting for words we're referring to mathematical Boolean operators. So I'll be talking about like stylized and. See how it's like emphasized, like A-N-D. But when referring to logic gates, the word will be stylized like this. And, okay? In general. They like mean the same thing, but you know, it'll help, I think. Oh, are we talking about a logic gate? Are we talking about a Boolean operation? Or are we just using the regular old word and? Okay? All right. AND gates. Well, before the AND gate, let's think about what does AND mean. All right. I have two variables here that can take on the values 0s or 1s. So here's the four possible combinations of those values of A and B. And what is AND? Well, if we see 0, 0, I should get a 0. 0, 1, I should get a 1, 0. 1, 0, I should get a 0. And 1, 1, I should get a 1. So only when they're both on should I get a 1. Okay? Now, before we jump down, take a moment and think about what we just saw with the transistors as switches. Okay? Take a moment and think. Imagine this A is a switch that can have a state 0 or 1. B is a switch that has a state 0 or 1. Only when they're both on should I see any output. So think, what should that look like? All right, too many late people. This is the last warning you get. You show up more than 5 minutes late, you're getting shown the door. You're not coming in here, okay? So, only when they're both on should I see some output. So think about what we just saw. I'm going to go back to the original image. Okay, obviously this is where, okay, I only have one switch, like an A. But imagine I had two switches. What could I design that looks something kind of like this, using more transistors, obviously more inputs and whatnot? How could I design something like this to perform that operation, that AND? Take a moment and think. Seriously, just think about it, because I'm willing to bet you could figure this one out. Here's the thing, it's probably simpler than you think. Raise your hand if you have an idea. Two people, really? I thought maybe more of you would. You're thinking too hard, probably. Well, how about this? Raise your hand if you're like, yeah, that's totally what I was thinking. 2 people, 2.5 people. 2 2/2 people. Okay. Right? Look at this and make it make sense. I do not think that anything here is making you take a logical leap. Is making you take a leap. You definitely can understand this. Like imagine I have water here, and they're both off. Will water get down here? No. Imagine, in fact, let's think about this in terms of that like short circuiting or that like annihilator property. Remember that annihilator algebraic property about like with and? False and I don't care, it's false. If this is off, do I care if this is on or off? No. I mean, you could even see it like physically, right? So there's a charge here. It wants to go down here. Think of it like water. Water's up here. But this valve isn't open. The switch isn't on. So the water's just stuck. It won't flow. I turn one of them on. Okay, water gets to here. But if this is still off, it's stuck. If this is off and this is on, well, it's still stuck up here. But only when they're both on. Only when both valves are opened will the water go down, build up, and then flow out. Right? This should be very obvious to you. If not, we're going to have a hard time. Okay? I know you like, oh, transistors are a new idea. Just think of them as the more abstract idea of it's a switch. Cool? All right? So what do I say here? With two transistors in series, this is what we call it. When you put things in series, they're like in the same line. Okay, they're in a series. Both need to be on for the signal to travel through to the output. Series means one after the other along the same conductor, conductor meaning wire. In a series circuit, the signal can only travel along a single conductor. If either the switches or both are off, the signal obviously cannot possibly travel to the output. Both need to be on, right? This beautifully corresponds with AND. Do we agree? Good. And we call this circuit an AND gate. Now, one thing to note here that is, I think, an important observation. It might not be obvious why it's important right now, but it is an important observation. Notice that, and like I said before, these signals are isolated from these signals, from this signal on this side, okay? When I have an AND gate and I have like, okay, input, input, and there's an output. The charge of this output is not from these charges. It's caused by those charges because those charges turn on the gates. But ultimately, the charge that gets outputted came from up here. Okay? Similarly, if these gates are off, the fact that there's no charge here has nothing to do with the fact that there's no charge on here. I mean, it does in the sense that the gates are off. But it's the fact that it's connected to ground. It's sunk to ground on this side through the pull-down resistor. Okay? The transistors are the charges on the gate part of the transistor are isolated from the charge from the source to the drain. Cool? Happy, sad, angry? Yes?
So if there's no power from the source, the two and the AND gate would be both on.
And it would still be, it would allow whatever charge is up here, could be a 0, to pass through. Well, I mean, whatever. If there was no charge up here, you're absolutely right. A lot of people tend to like think, I'll come back to this very, very shortly. Okay. Yes. And I did mention this last time, but I'll mention it again. You'll notice that in most of the circuits I show you and provide to you, there will be a test component. And it allows us to create unit tests for the circuits to help ensure correctness. Although the unit tests get more complex and expressive, a simple form of unit test for digital are truth tables. Most of them are going to be effectively truth tables. Below is unit test for the AND circuit, which is a truth table defining how the circuit should behave by how Boolean AND works. So like if I right-clicked on this test, I'd get a box like this, and I can say like edit. And this is the truth table. And A, like it works on the labels. If I don't have a labeled input, it ignores it. And B, and O, A, B, and O for out, whatever. You'll notice like underscore A, that's common math, like that means like subscript, right? And that's how, I mean, look. See, it's like test underscore and underscore test and lower, that's that, right? So it's kind of neat. Anyways, so what's this truth table? Well, if they're both off, 0, 0, we should get a 0. 0, 1, we should get a 0. 1, 0, we should get a 0. If they're both on, we should get a 1, right? So these circuits will, they're tested, right? If I design this circuit wrong, but I know how it's supposed to operate as defined by the unit test, and I run the circuit, and the circuit doesn't match the unit test, something's wrong. Maybe I made a mistake with my unit test, or maybe there's a bug in my circuit. I found a huge bug yesterday, oh man, in my big circuit design for the whole computer that we're working towards. Now I have to go back and fix everything. It's going to be a nightmare. But it's because I didn't test well enough. It's foolish me. Yeah. So be aware that's what these are, and you'll see them, and you should look at them, and you should write them for yourself anyways. Okay. Boolean operators are used so extensively that we're going to form an abstraction level, okay? If I'm drawing, if I want to like draw for a circuit diagram the AND gate, I'm not drawing this, okay? I'm not going to draw that. Because, okay, look, it's not that complicated. But when we're building like digital circuits like this, we might be drawing a lot of AND gates. So I'm not going to want to draw all of that. Instead, what I draw is that. Okay? It's got inputs and an output. That means AND. Okay? If I see 0, 0, I get a 0. If I see 1, 0, 0, 1, I get a 0. If I see 1, 1, I get a 1. Okay? So this is our first layer of abstraction on the like circuitry side. And is just these two transistors in series. That's what it is physically. But we're going to draw it like this because that just saves us a lot of time. Okay? Boolean operators are used extensively within computer architecture. We have a special symbol for them. Below are two images for the symbol for an AND gate. The first image is just the AND gate symbol. And this here shows you like how I would configure it to match what we just saw. Okay? Notice, so what's included here? The AND A, the AND B, and the output. So the two inputs and the output. So the symbol must mean everything else. It must mean like all this stuff. This is, in this symbol, I don't see anything connected to ground. That's fine. I don't see anything connected to a charge. That's fine. We know they're there, but it doesn't matter for our needs. And often, students, when learning this stuff for the first time, they lose sense that like, if this is on and this is on, if I have a charge coming in and a charge coming in and they're both on, and I have a charge going out, it might feel like, okay, so like these charges go out here. No, they don't. These charges controlled whether a charge that, you know, kind of did really come from somewhere else goes out. This is not like, if you don't understand this, you're in big trouble. But it's important because it does come up, and we'll see examples of this soon about like why it's important. But note that the charge that comes out of this, although is ultimately like caused by this, like this impacts whether or not the charge comes out, the actual source of that charge is from somewhere else. Okay? We don't draw that and that. And it's funny because I think you asked me like yesterday, like are they always connected to ground? No, we very quickly stopped drawing ground. Okay? Cool. So this part here, to be clear, this part here is the match to like this. Okay? These are equivalent. Any questions about what we see here for AND? All right, like I said, this is the first major layer of abstraction that will be seen through the course. Instead of thinking of logic gates in terms of their whole schematics with transistors, they are represented as a single symbol because obviously I'm not going to draw everything out. You can think of this as like this is now, if we're writing code, this is a function. That means the transistors, but we've like now created a layer of abstraction with a function. Okay? Okay. We now, like, and I want to make sure you have an appreciation for what we just did. We have created, I'm willing to bet you can guess we're about to learn how to make OR and how to make NOT, right? But we just implemented physically, we could physically implement, I realize this is images on a screen and we're doing it in a simulator, but this is all based on what we do in real life. We can physically implement AND. OR gate. Well, here is what the OR truth table looks like. 0, 0, we get a 0. But if either of them are on, and both of them are on, we get the 1 output. Now, here was the AND gate. I'm going to give you a minute. Think long and hard. If that's the AND gate, how could I make an OR gate? Right? Going back to the truth table 2, how could I configure transistors? We're talking about transistors again. I know we just took a level up, but now we go to OR. We start back with transistors. Think, with transistors, how can I configure them to do OR? Just think about it. I don't want an answer right now. Just take a moment and think. Raise your hand if you have an idea. I'm not asking if you have an idea that you're 100% sure is correct. I'm asking, do you have an idea? Be bold, raise your hand, come on. Come on, everybody except you two, come on, you've got an idea. You have no idea? Well, is this what you kind of thought? So, yeah, maybe, close enough. Yeah. Now, okay, when I say, to be clear, what I ask is like, is this what you want? The actual like physical exact layouts don't matter. What matters is I have a transistor, I have like a breaking line. And there's a transistor in each controlled by a switch each. That's what's important here. The fact that it was designed and drawn exactly like this, that's not important, okay? What's important is that it breaks, and we have the transistors in separate lines. If the previous circuit was called a series, if things were in series, does anyone know what we call this? Parallel. Raise your hand if you're like, yeah, I heard that word before. Yeah, it's parallel. They're in parallel. Let's think about that intuition again. I've got water. Both of these switches are off. Can water flow down to here? No, meaning that this is 0 because it gets pulled down through the sink. There's a sink, no water's on. If there was any water left in the sink, it's drained out slowly. There's nothing in that sink. If I turn either of these taps on, if this one gets turned on, all right, the water goes down there and then fills up and goes. If this one's off, but this one's on, all right, the water flows this way, fills up and then goes. If both of them are on, whatever, it doesn't matter, they go. That's OR. This configuration. When talking about circuits, series and parallel, they're like the flip side of each other, right? So there's almost like this like natural like aesthetic. I don't know how else to describe it. It's almost like you've got this AND operation, and it's almost like there's like almost like a beauty, for lack of a better term, of how OR, like the other one, and an OR is like that other design. I don't know. There's something about it to me that's just kind of nice. So that's OR, A, B, and the output. You might think, well, if both are on, is more going to flow? No, it doesn't matter. It's on or it's off, whatever. Cool? There's still a maximum throughput we can have because of the diameter of the pipes, whatever. Questions about this? Thoughts, concerns? Again, the charges on here, although impact whether or not the stuff can flow from the source to the drain, the actual charge from the output's ultimately from there. By the way, when drawing this, like it would have been entirely possible to like not have these connect right here. I could have had two separate lines that go to the power. It doesn't really matter. I just had the one. Yeah?
The two separate lines, would it be an exclusive OR then?
No, it would not. They would still, they're both, usually no, it wouldn't be exclusive OR. Exclusive OR is a little bit more annoying, but I'll make you do it on an assignment or something, so you'll have fun with that. No, it wouldn't be. You would assume that the charges would be the same on them anyways, and often you would even assume that, okay, I drew them separately, but let's assume they all come from the same source. It's just kind of like a design thing. Yeah. Interesting question, though. Other questions? So now's the time to ask. Like when you look at this, I hope like this is the simple. This is like the lowest level of simple. When I say simple, I don't mean trivial. Don't get it twisted, okay? Simple is not the opposite. Simple is like the opposite of complex. But again, complex doesn't necessarily mean like challenging. It's just like it's complex. But there might be a lot of order to it. So it's simple, not necessarily trivial, but there's nothing wild going on here. Yeah?
Would it be any different if you had the output connected before the two wires kind of met?
Before they met up here? No, it wouldn't, no. Because it would still flow out that way. It wouldn't. Interesting question. I'm going to restate his question, because it is an interesting question. I drew the output like here. But what happens if, like, what if I actually connected it to, like, here? Right? Would that matter? No. Because as far as it's concerned right here, although it branches, this is all one conductor. It's all, like, the same. If there's the charge of, like, 5 volts here, it'll also be here, and here, and here, assuming no resistance, but the charge should be the same. The charge would be different on this side of the resistor, but the charge on this side is it's the same no matter where it is. Yeah. Interesting question, though. Very interesting question. You could also, just one sec, you could also like think of it like the water example too. If this was over here and the water was coming down here and it just kept filling up, it would eventually like fill up both sides and go out. I mean, unless there was like a vacuum where the water pressure or the air pressure couldn't go, and there was but let's assume there's no. Let's not bend this analogy too hard. Yeah.
I just want to be sure. Does both inputs have to be on the left side?
No, they don't. That's entirely. That's all that matters is that wherever this is, hopefully that's clear to people. All that matters is wherever this switch is, It could be over there for all I care. As long as its wire comes and connects to here, I'm happy. Yeah. And digital will be happy as well. Good question, though. These are things that you'll kind of figure out once you play with digital, what's required and what's not, but good question. Any of these circuits, if you've forked the repo, they're already in here, but you can go download these circuits directly from the GitHub page. Like, I'll show you in one moment. Where's lot logic? No, 1, 2 decoders, 2 functional, no. Transistors, gates, transistors, operations with entry. Okay, maybe this is what I want. Yes, okay, okay, it's all in one. So here we go. Here's our, oh no, don't look at the other one. No, 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 don't look. Don't spoil it. Oh no, come on. So for fun, let's move it over here and move this one there. It's fine. Yeah, cool. Okay, and if we go to the GitHub page, which is linked right at the top of the website. This is the GitHub repo. This is the repo that builds this whole course. If you go into like, okay, site, and this is the same file system, like file folder layout I had that I was just navigating, by the way. It's not the same. It's the same thing. It's because I'm navigating it just in my browser versus in this browser. Topics, and that was transistors, gates, and Boolean operators with transistors. This is it. I mean, if I click on it, it's just going to be a bunch of like markdown. That doesn't make sense. But if you open this up in digital, you would see what we just saw. So they're all available there. There's a lot of these things that you could just get from the course website. By the way, assignment 1 will be out soon. I'm going to try to get it up today. If not, I'll have it out for you on Monday. The first assignment's not going to be, like, as I haven't made it yet, but I don't envision the first assignment to be a big one. Raise your hand if you've had me before. Okay, so if you've had me before, you know how I like big assignments, right? That take you at least like 10 hours to do, right? I'm sorry to disappoint you. I think that these assignments probably won't take you nearly that long. I don't know. I'm wrong. This is the first time I'm teaching the course like this. I could be way off. I don't think they're going to be like that. But do note, like, oh, and because of it, for this first assignment, I usually like to give people 2 weeks for assignments, but because of the scale of these assignments, I'm probably going to give you 1 week for this one, but we'll see. I have to get it like made first to really know what it is. What else do I want to say about it? On some of them, I might be like, okay, make AND with transistors. Yeah, you can go download it from the course website and implement, but there's like 5 components. Just build it, okay? What else? This first assignment stuff, it's gonna have like 2 main parts. One part's gonna be more of like one part's gonna be in digital, the other part's not gonna be in digital. It's gonna be things like playing around with Boolean or binary numbers a little bit. All your submissions though need to be like done on a computer, so no like handwritten submissions. And they need to be submitted as PDFs. So if you're like, but I use Microsoft Word, that's fine, save it as a PDF. You can do that. And if you can't, print it as a PDF. Fine, you can do that. Also, you have to use proper math typesetting though too. If you don't know how to do that, take 2 minutes and figure it out, and you'll do yourself a favor by doing that. You'll do yourself a favor in that it'll get marked if you do. It won't if you don't. And also because it'll be handy for you in general. But these details will come out later. I haven't made the assignment yet, really. I'm only getting some ideas down at this stage. Anyways, back to course content. Any questions about that real quick? All right. Yeah. All right, and what would not look like? Oh, wait, hold on. And then, so there's OR, and they're in parallel. Okay, I just want to make sure I'm not missing anything. With two transistors in parallel, either would need to be on for the signal to travel through, either, or both. Parallel, meaning transistors are separated and they're like in parallel, right? They're going beside each other. They don't literally need to be parallel, fine, but you know, the fact is they're not in series. Not in series is parallel. In parallel circuits, the signal can travel on each of the separate lines. And below is the symbol we draw for OR. Okay? This is AND. That's OR. Okay? I know that one looks nicer, whatever, just good enough. Okay? What matters is this part. The shape of this. Okay? Okay? Okay. Now, both AND and OR had two inputs, right? So when we think of the transistors, how the transistors are laid out, we had two inputs. But NOT is a unary operator. It works on one input. So I only really have one switch, right? One toggle, on, off, right? So if we think of NOT, if A is 0, not A is 1. If A is 1, not A is 0, right? So there's no 2, I only have 1. But how on earth could I do NOT with transistors? In the same way, like I did OR and AND, but how can I do that with transistors? Take a few seconds, I'll give you a minute, and think. Think about it. Try to get an idea down. If you want to sketch it on paper, by all means, you don't have to hand it or anything. Just, think about it. You may have saw it already in the example I showed, but whatever. There are a couple of ways. Well, first and foremost, how many ways are there to solve a problem? Come on, I'm looking for a precise answer. Pardon? An infinite, right? So, okay, fine, fair enough, fine. Now, some of those are going to be better than others. Like those ands and ors that I showed you are those are nice, simple, clean ones, right? But we could do it other ways. With NOT, I would say there's two obvious ways to do NOT. Obvious is, in the eye of the beholder. But one of which I'm going to say we really don't want to use. We could, but we're not going to for our purposes now. But take a moment, think about it. I mean, right now, raise your hand if you've got an idea. Okay, take a moment and think. I want everyone to have an idea in their head. You don't need to be right. I want you to be right. You don't need to be, but think. How could that look? Okay, raise your hand now if you're like, okay, I've got an idea. Now, one way we could do this is, remember how I was talking about N and P channel transistors, right? Where N, that's the one we've been using, where if you have a charge, it allows the stuff to flow. So why don't we just switch it to the other one, the P channel, where if I don't have a charge, then it flows, and if I do have a charge, it turns off. And that's entirely fine. Raise your hand if you're like, that's what I was thinking. Okay, good job. Now, we don't want to use that one though. We can, there's nothing wrong with it, but let's all stick with just N-channel transistors. I like them a little better. So how can we do that? And this one, I'm going to warn you, is actually, you might look at what I'm about to show you and think to yourself, Yeah, that's kind of what I was expecting, fine, whatever. Or you might look at it and be like, that feels a little bit more complex than I anticipated. This is all new ideas, so you're both right in that case. But what does it look like? Well, here's how we can do it. Take a moment and look at this and try to make sense of like what's going on. Because it is a weird one, because it's definitely like a little different from what we saw before. Apparently the output is before the gate. What? Yeah. So what's going on here? Well, when this gate is off, so first of all, that's another n-channel transistor, meaning only when there's a positive charge does this turn on. But think of it like this. When this is off, the water can't flow. And it backs up and flows that way, right? But as soon as we turn it off, it's like we open the plug. We open the drain, and the water goes straight to ground. And because it's going straight to ground, it cannot back up and flow out. It just gets straight, it gets sunk straight to ground. So it's kind of like pulling out the world from underneath it and it just falls. That's what's happening. Okay? Now, this here is not using a pull down resistor. Who wants to guess what we call that configuration? It's not pull down, pull up, right? Why pull up? Well, it's kind of the same idea. First of all, we need to have a resistor. But also, when this is closed, this whole thing gets pulled up to be fully charged. But as soon as this is connected to ground, this connects to this, meaning this becomes like one wire. There's a transistor there, but it's connected. So this is one wire, and the whole charge on this side of the resistor gets sunk immediately to 0. This, on the other side of the transistor, it has the charge. Okay? Having a complete understanding of this like resistor charge is not really important. What is important is just being aware, like, okay, it's connected. Okay, the transistor, or the resistor kind of like blocks the charge. That's kind of a bad way to put it, but I think we're okay with that. Cool? So how do we draw? Okay, notice how the output is on the source end of the transistor. This is because the output should be 1 when the gate is off. I just looked at the projector and now I can't see anything. Oh, my goodness. Ugh. This is because the output should be 1 when the gate is off, but as soon as the gate is on, the output becomes 0. If it's unclear, think of this. When the transistor is off, the signal from the voltage source through the resistor is connected to the output. When the transistor is on, the output would be effectively directly connected to ground, syncing the signal to 0. Okay? And then I've got the example of if still unclear, consider a plugged sink with the faucet running that is overflowing. Here, though, the plug, in previous examples, when we were talking about and or, the sink was never plugged. We had like padding in the drain. That was the pull down resistor. Okay? Now think the padding's in the faucet. Okay? We turn it on, and the sink fills up, slowly, but it fills up. And it's overflowing to the output. But the rate in which the charge, like the water is filling up the sink, is not that high. I turn on the transistor, I open up the plug, I open the drain, open that valve, and the water can flow. And the rate in which the charge is coming through that transistor is too slow such that like the water still drains out of the sink. That's like the intuition there. If someone removes the plug from the drain, the water can flow through the drain and stop overflowing. This would be like what happens when the transistor is turned on. And then here's the other How could this configuration, if we used a P channel instead of an N channel? Well, we already kind of talked about that. Below is how we draw a NOT gate. Now, I will show you something that's kind of annoying. Annoying is not the right word, but if we were to show like a NOT gate, here's NOT. For some weird reason, and I don't know why, the NOT gate in digital, the default, if you go in here, is the not wide shape. This is the wide shape. This is the normal thing here. Is this triangle with the circle. Now, really, so okay, that's a NOT gate, right? If this is 0, the output of this is 1. But remember, the source of the charge that's being output is not this. I mean, obviously this is 0. It's from some voltage source, some else, right? Right? Because remember, this is connected in some way itself. We just don't draw it for simplicity. Now, one thing to note here is, really? You're like, okay, this is a NOT gate. Well, really, I mean, really, but not really, but really, but not really. It's the circle that's like the NOT. The circle means NOT. The triangle really means like a driver or a buffer or something. And they don't have any functional meaning in some cases. But to draw a NOT so things don't get like messed up, we just threw it through some like driver with a 0, whatever. It doesn't matter so much. Point is, the circle is like NOT a lot of the times, and we'll see that pop up as we go. Any last questions before we wrap up for today? All right, I'll see you all later. Have a wonderful weekend.